Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'd like to introduce Tiberio Caetano, who works at National ICT in Australia, where I also work. So he's comes from Brazil originally via way of Calgary.
Edmonton.
Edmonton. Sorry, Edmonton, Alberta. Yes.
Yeah.
So extremes of temperature. He did his PhD there and graduated in 2004 before coming to work in Australia. Now I hired him into the vision group there, but he jumped ship into the machine learning group at some point. So he has expertise in both vision and machine learning, and I think he's going to give us a bit of a talk which bridges the two areas today.
Thanks, Richard, for the introduction. So essentially, I'll try to divide this talk in two parts. So the first part will be a very generic talk about the type of work we are doing in computer vision, and essentially using machine learning methods to solve computer vision problems. And the second part, which is probably going to be a little bit shorter, is basically going to be a bit more specific about one recent project. Okay? So I would like to thank my collaborators. So this is Rogério Ferres from IBM, TJ Watson Research Center, some of my PhD students here, Julian Macaulay, Javanshi, Cockley, the Cheng over there, Longbing Chen, Alex Moller here, collaborators involved in these projects here that I will describe. I think I've missed the picture of Dale Schurmans, who is another collaborator in these projects I'm going to present to you. Okay? So as I mentioned, I will divide the presentation in two parts. So the part one will be essentially preaching structure prediction in computer vision. I'll quickly describe what this means and give examples of this. The second part then will be a little bit more specific about the recent work we've just submitted. Okay? So let's focus on the first part, structure prediction in computer vision. So this part I'll first talk about what I call easy vision problems. And so here's an easy vision problem. I want to find the class of this object. Okay? I'll say, okay, this is a bike. I'm calling this an easy vision problem. So imagine what I would call a difficult vision problem. So here's yet another easy vision problem. What's the class of this object? So I find it easy, so that's a car. It's a very typical car. So. And yet another easy vision problem. What's the class of this object here? So that's a ship, also an easy vision problem. So this is the design of a new ship that's going to be around very soon. It basically has a very sophisticated hotel in it. And, well, you need to actually arrive at it by plane. But yet, it is a ship. So these are easy vision problems. Okay? I hope you agree with me that these are all easy vision problems. So for these easy vision problems that are classification, right, you can do two things. A very traditional approach that would be popular in the 60s and 70s is knowledge-driven approach. So something like this. So this would be rule-based, model-based, grammar-based. So you would represent parts of the object as object parts, and basically you would create a model, a complicated model, to try to represent the model, the object, and try to figure out what the model, what the object is, whether it's a ship, whether it's a car, or whatever. So this was popular in the beginnings of computer vision. So you would typically have complicated descriptions of objects, and no data leveraging, or almost no data leveraging whatsoever. So if you look at how things have been happening more recently, things have been basically been changing from a knowledge-driven approach to a data-driven approach. If you want to do classification these days, so for example, one option is to use things like support vector machine technology, and that basically has driven most of the activities in classification computer vision recently, in the 90s and recent years. So essentially, the idea here is that instead of going for those complicated models, you go for very simple models, but yet you leverage data heavily. So the question I have for you is, what would you do? I mean, would you go back to this age here and do complex models and no data leveraging, or would you, just continue what people are doing at the moment with simple models and huge data leveraging? So what would you do? That's a question. I mean, you just continue doing this.
That's too boring.
Huh?
That's too boring to just keep doing what you're doing. So.
What's too boring?
Maybe do the first one.
The first one is too boring. Okay, so basically this is what almost everyone is doing, right? Okay, so let's focus on the second approach here. So there you go. I mean, one option if you want to do simple classification, again, just remind you, we are working here on simple vision problems. Okay, you want to do simple classification, one option is you just use support vector machines, extremely well-known and very successful classification technique. Okay, and there you go. Well, you don't need to do support vector machines. I mean, there are many ways to do classification. One way, for example, is to do logistic regression. Instead of learning the boundary, you just learn these discriminative functions separately, and then you decide according to the intersection of them. Okay, so this is something called, for example, logistic regression. Also a discriminative approach, but still based on density estimation techniques. And there are many other things you could do. Okay, why am I calling these problems easy vision problems? It seems I'm being arrogant here. But they are easy vision problems in the following sense, because the output is very low dimensional. It's the number of classes. For example, I want to classify an object. Well, I may have 2 classes, 10 classes, 50 classes, even 100 classes. But I would call this extremely low dimensional. Okay? Well, we usually think these problems are difficult, not because the output is low dimensional, but because the input is high dimensional, because images are very complicated objects. That's why computer vision is difficult. But my point in this talk, one of my points in this talk, is that, of course, this makes life difficult. That's true. But this here makes life not as difficult as it could be. If the output were also high dimensional, then we would have the really hard vision problems. Okay?
Some variants of recognition today, people are starting to talk about labeling pixels, actually doing segmentation together with recognition.
Yeah, that's the point of this talk. But the recent variants of that. I'm just trying to draw basically the mainstream up to recent years, and then try to survey the recent years and do what has been done in the last couple of years. Okay, but that's a fair point. That's the point of this talk. Okay. Okay, so inference here is trivial. What I mean by inference, you want to predict the class membership of a given image. Okay, so basically inference is trivial in the sense that, well, for a support vector machine, you just check which class has highest margin score. You can enumerate the classes because you have a very small number of classes easily. And logistic regression, you just check which class has higher probability under your individual regression functions. Okay, so now let's talk about hard vision problems, which is what Rick mentioned that people are doing. So this is a hard vision problem. Depth estimation. You here have, okay, Tsukuba image, well-known stereo pair. Here have the ground truth for this. Okay? Why I'm calling this a hard vision problem? Because the input is high dimensional, but the output is also high dimensional. The output is another image. The output is not a simple class label. It's extremely high dimensional. Likewise here. So the input is an image, the output is yet another image denoising. So could you get from here to there efficiently and with high accuracy? So that's a hard vision problem. Another visual problem, image segmentation. So there you go. Input is an image. Output is very high dimensional as well, another image. Okay? This is bad, because this is my favorite theme, which is matching, and the image is not showing up. Okay, no problem. I'll show later an example of matching, this graph matching case. Basically what was up there is basically a pair of images and matches between features of those images. The input is a pair of images, and the output is also something very complicated, which is a permutation of the nodes of specific points.
Right, but dimensional analysis doesn't capture everything, right? Because adding two images together is basically high dimensional input and high dimensional output, and that is an easy problem, right?
Can you ask
two images
yeah.
and taking their average, right? That's a high dimensional input, high dimensional output. So just classifying things by dimension doesn't really tell you what the hardness is of the problem.
Not sure I'm getting your point.
You're saying what it makes a hard problem? A hard problem has a high dimensional input and a high dimensional output, right? The problem of taking two images and computing their average satisfies your definition of what a hard problem is.
No, don't take this too strictly. Okay? Don't take this too strictly. This is more pictorial kind of description of what I'm talking about. Okay? So essentially, you can also, in principle, think of two generic approaches, like we've mentioned previously, a knowledge-driven approach or a data-driven approach. For this class of problems, okay, you can qualify this as differently. I'm just using easy and hard just to make you remember one month from now that you've heard easy and hard. Because if I had used other qualifiers, you wouldn't remember. So the question is, what would you do? So my point here is that for these hard vision problems, people still are playing this game here, mostly. Okay? Most approaches are knowledge-based. So for example, energy functions are typically handcrafted. Examples: MRF for stereo, MRF for segmentation, graph matching, and a bunch of other discrete optimization problems. Where your output is complicated, you have a very sophisticated predictor. Instead of just a support vector machine that you are basically instantiating each one of those classes and checking which has highest margin score, you have to run an entire complicated algorithm in order to make a prediction. Like here, well, you need to solve an MRF. Here, you need to solve quadratic assignment. Here, and other things. So you work really very hard at trying to find the best solution for a model that you don't know in the first place, that's the right model or not, because you just handcraft these energy functions. Okay? So good inference, my point is, so good inference is not enough. We need to learn the energy functions themselves. That's what we should be doing. So basically, if you were an advocate of the data-driven approach for the easy problems, why shouldn't you be an advocate of the data-driven approach for difficult problems as well? So there is an inconsistency there. So that's what we need to do. So we need to find good solutions to the right problem, not to the wrong problem. And the questions are, so why should we be working so hard to improve inference incrementally, which is what a substantial proportion of the vision community is doing in discrete optimization, when we know that the global optima are poor anyway? I mean, it's so much effort doing this. I mean, to me, it doesn't make much sense. Why bother so much while being so optimal when the criterion being optimized is simply a reasonable guess of what a good criterion would be? So I think we should be asking those questions. So here's an example. This is a beautiful example from a paper in 2005. So here's the original image, Tsukuba image. Here's the ground truth. And here's the global optimum according to a simple pairwise MRF with handcrafted parameters. So look at the differences between this and that. So this is the global optimum of the energy function. So this is what people are really writing more and more papers to achieve this result here. And when you compare this result with that result, you see that this is really crap. If you be extremely picky, this is crap. Look at the camera. There's no camera here. I can't see any camera. So, I mean, shouldn't we be balancing a little bit more how much we are working hard on finding the right solution to a given problem, or finding the right problem, the right question to be asking in the first place? So here, are a bunch of other examples of this very issue by Meltzer, Yanova, and Weiss in ICCV 2005, where here you have a bunch of images. Here you have a solution obtained with belief propagation. Here's a solution with graph cuts. And here's the global optimum. They actually managed to find the global optimum for a specific MRF, pairwise MRF energy function. And then if you look at the global optimum, they are really not, in some cases, they are quite far from what a human labeler would provide. So why are so many people concentrating their efforts on optimizing optimally this energy function if at the end you are going to get something that's not that good anyway? So here's something I want you to think about. So in red, you have the quality of an algorithm. So here's the level of sophistication of an algorithm. Here's algorithm 1. Here's algorithm 2. This is every point in this line is a single paper in ICCV or CVPR. So people are walking this direction here. Okay? So algorithm sophistication. So this red line here, you have the quality with respect to a poor energy function. Of course, that's improving. Okay? In this blue line, you have a quality with respect to real perception. That's stuck. That's stuck. That's stuck. It has been stuck for a long while here. And yet people are publishing papers and being paid for publishing those papers. Okay? So what's the point?
Is that a problem with the data set?
Well, that's... Well, exactly. So people are taking these energy functions for granted, right? And of course, you are improving with respect to that energy function. But so what? That energy function was handcrafted in the first place. You're being extremely religious here. Come on, we are scientists. In the machine learning field, learning energy function has a name. It's called structured estimation or structured learning. Okay? Inferring a global optimum of a given energy function is called simply inference. This has the same name in computer vision. Okay? So when people talk about structured prediction, they are really talking about the whole business of predicting high-dimensional output and doing learning in the process of doing so as well. Not only handcrafting those energy functions, but doing learning, leveraging data in order to find what would be the right problem to be solved in the first place. So what would be popular estimators? In the beginning of the talk, we discussed support vector machines and logistic regression. So likewise here, people are creating extensions of those models and of those estimators, actually, for the structured case as well. Today we have something called structural support vector machines, so which is a cousin of the SVM, okay? Structural SVMs. So basically, these two references here is basically what you need to look at, which are the papers that introduce essential tools of how to do learning when the output is very, very high dimensional. Because we are talking about really high dimensional. Imagine an image. You cannot enumerate all possible images. And yet, that's the number of classes you have. So how do you solve that? The learning problem becomes extremely difficult. It's much more challenging than doing inference. Likewise, you can do something different. You can ask what's the analogous of logistic regression for this structured case. And that has a very popular name. It's called conditional random fields. That's only logistic regression for a different feature vector. Yes?
You mentioned that the cost function in previous matching or stereo is not correct. But how do you guarantee that structure SVM, cost function or structure SVM of conditional random field is correct? Has correct cost function? Because you
no, because you just train against labeled data, right? Yeah. So you can have, for example, what you have these days. You can have good either hand segmentations of correct stereo, okay?
But I mean, you can learn parameters to fit that model. But for example, the conditional random field, you still define the potential functions. You must assume.
No, you define the features. Yeah. You don't define the. You define the model class, and then you search which element in your model class maximizes the evidence of the observations. Whereas in traditional models, you just select a element of your model class. You just select, you handcraft your parameters. So therefore, if you have a large model class that you would realize the entire model class by changing your parameters, you don't explore that entire model class. You just fix a single model and you believe that that's the best thing you can do. Then you work extremely hard at optimizing it. Yes?
So If you're going to address this later, just ignore my question.
Uh-huh.
But what about learning parameters in MRFs, like Marshall Tappan has learning parameters?
Sure, but what's being, absolutely. But the point is that you want to optimize those parameters to minimize the final loss, which is, for example, the loss of stereo.
Right.
For example, a Hamming loss between what you are predicting, let's say, and a hand label, just in a product between. And minimizing that loss can be tricky.
It can be very challenging. I mean, that's one reason is because Marshall worked with Gaussian MRFs. It was tractable, but he was doing, he could do image denoising where with synthetic training data, he was optimizing the loss between the final, the learned MRF and the final output.
Well, the basic problem you see is that if you want to really minimize a loss that's interesting, like for example a Hamming loss, that loss is discontinuous. Yeah. So you have a piecewise constant optimization problem. There's no hope of using any smooth optimization techniques to solve that. So what I'm going to show that these instead optimize likelihood, which is something that people are more familiar with. Logistic regression, I mean, everyone knows how it works. You just create a more sophisticated model, then you have a complicated partition function to solve. But that has a problem because you have the problem of computing the partition function. But this is an interesting alternative because here you have no partition function issue. So you just look at the boundary. You just look at a few examples. And this will be much faster than this in general. And what's the principle here is to upper bound that crazy objective function that you have. Because you have the ideal loss you want to minimize would be a very crazy Hamming loss, which is piecewise constant. I mean, there's no really way to do that efficiently. But if you have a decent surrogate loss that kind of preserves the structure of that original loss, and that surrogate loss is amenable to efficient optimization, that's what this is all about. And this has actually been extremely successful. Although the first paper that I know of that used this in computer vision was only 2005. But now we did this in 2007, and then now people have suddenly realized, yeah, we really need to do this stuff. Okay? Conditional random fields people have been using for a bit longer in computer vision. So this was first proposed in 2001, but has very nice statistical properties. So this is a consistent estimator. This is not consistent estimator, for example, but has serious problems because of the partition function. You need to create an entire probability distribution on the images, and that's when you want to learn, you want to do gradient descent, then you need to estimate the partition function. It's really bad. So this seems to be a very practical alternative, the first one. So both have advantages and disadvantages. Okay, I'll move forward here. So just one example, graph matching here. So the graph matching problem is really a hard problem, right? So if you want to take into account pairwise constraints, for example, you get a quadratic assignment formulation. And that can be really hard. So the point is that traditionally people just handcraft these objective functions for graph matching, right? You just say, look, I mean, these unary similarities will look at shift features. These quadratic similarities will look at relative distances or whatever. And then you just fix parameters, and then you work really very hard to solve that combinatorial problem. And you didn't know in the first place whether your objective was good or not. So the point is that you can actually learn those energy functions. So in this work, for example, we use structured SVM to solve those energy functions. And then we find some very nice things. For example, I mean, you can model graph matching with complicated combinatorial settings, like quadratic assignment, or you can model graph matching simple combinatorial settings, like linear assignment. Only look at matches between individual pixels instead of having pairwise constraints. And that's a tractable model. It turns out that if you learn that simple model, you obtain results which are as good as you would have obtained with a complex model without learning. This is something we figured out in these examples here. This is what you get. If you model graph matching, for example, as linear assignment, which is efficient to compute, it will perform similarly with quadratic assignment without learning. Why? Because you are finding the right weight of the shift features, for example, in such a way that your final result is what you want it to be because you have training data. So you engineer it. So basically, you automatically tune the relevance of your 128 shift features, for example, so that that joint weight will, when you solve this combinatorial problem, produce an image that is what you wanted to produce because you have the output, either by hand labeling or by laser scans of, for example, in the case of depth estimation. Okay, so this is one example. So okay, so here my matches are up. So this is my favorite subject, graph matching. This is just to show that, okay, in green here you have correctly matched points. In red you have wrongly matched points. Okay, this is exactly the same model class. It's just that here we have handcrafted the matching score, and here we have learned the other way around. Sorry. So here we have handcrafted, and here we have learned the matching scores. Okay. So you see that there are many mistakes that you can avoid by just tuning what's the right model in your model class. Of course, here, how many classes you have? N factorial. If you, in this case here, I have 30 points here, 30 points here. I have as many classes as possible matches because my prediction here is the match. I'm predicting a match. So I'm parameterizing the algorithm that's producing the match. So it's like I have a support vector machines with 30 factorial classes. How do I solve that? That's why it's not trivial. And then you need to look at the paper to see these techniques that people are using. But the point is, you can improve. You can, yes, you can improve. So here another example that we have in CVPR this year, which is shape classification. We want to classify shapes, okay? So one thing that people do in shape classification, for example, is to use matching scores. To use the results of matching scores to do classification, because you know that sometimes, if you remember the paper by Belongi at ALIA in 2002 at PAMI, that was basically shape context features. I mean, probably many people are familiar with that. So what essentially they were doing, they were trying to classify objects based on matching scores, okay? But they were handcrafting the matching scores. So you handcraft the matching scores, you produce a match that's completely a function of how good was your matching scores. Then you parameterize the final matches. And then you learn after that stage. So you do this, right? You trust your matches completely. Then you do learning. After you've produced the match, you parameterize that and you do learning. But come on, I mean, you may be doing learning completely crap features here because you have done shape matching in the first place, completely trusting your uncalibrated linear assignment algorithm. So what we do in this paper here, we do everything in a single shot. So we optimize the matching score itself so that the classification loss is minimized. Okay? So here's an example of no learning. So you produce a matching. Okay, you can match this camel against this dog, but the algorithm has wrongly classified the dog and the camel as belonging to the same class. Okay? And here, if you do learning, so you use the matching as a means to classification, but you parameterize the matching itself. Then you can recover, you can say, well, these two guys are camels. They belong to the same class. Yes?
So there has been work on learning better feature descriptors or distances in feature space, things like that. I mean,
yeah, sure.
And you have training databases of correct and incorrect matches, right? So how does this work differ from just learning a better matching score?
Because this is optimizing the matching loss. This is not this one. This is optimizing, this is structural prediction. In that case, you are tuning your matching scores so as to minimize a very low dimensional surrogate. This is going directly to the output space and saying, look, I want this matching matrix, this permutation matrix. My loss that I want to optimize is the Hamming loss between two permutation matrices. That's extremely high dimensional. So you go directly to the problem that you really would like to solve instead of creating a surrogate low dimensional version.
Well, in that case, what they have is,
which paper are you talking about?
Simon Winder, Gang Hua, Matthew Brown. Here they've done a series of papers where they have SIFT-like features, or they're trying to learn better descriptors.
Okay.
And they have a database of which features actually match. There's several million matches of of patches that are known to be true matches and other matches that are known to be false. So they
Okay.
basically have a loss function, which is
Right.
correct or incorrect matching.
Right.
Learning it.
Right. So the question I have is, what's the algorithm that predicts what's the predictor in that case?
The difference, I guess, Rick, is that there you're learning how to make a single match.
That's right.
In this particular case, you're learning how to make complete matches.
So you're saying
It's a joint.
if you wrap a more complex algorithm around it, in
You
other
can
words,
still
you don't just
optimize.
have access to what's a correct match. You only have access to the final thing. You wrap your matcher into some other bigger black box and you evaluate the output of the black box. That's the difference, right?
I think the main thing is that I'm not optimizing in the scores of individual matches here. I'm not doing that. I'm optimizing the joint match, the quality of the joint match, because these 2 points cannot match to the same point here. For example, I have an injection constraint. That's essentially a bijection between these two there. So there are n factorial possible things that I need to optimize. I'm not saying, well, this guy is very similar to this one, so let's have a single parameter calibrating that. No. It's
Okay. No, it's you have a more complex system.
it's a more complex prediction model. Okay?
You don't know the ground truth of the mappings from one to the other.
You need the ground truth.
But you do know that?
You need to provide that manually, but can be an issue in many cases, but there are 2 ways to circumvent it. One way is to do a semi-supervised version of this learning scheme. In a semi-supervised version, you would provide a few matches. You don't provide the others, but you can still generalize the setting to marginalize over the hidden variables for the others. That's one option. The other option is, for example, if you're doing shape matching, if you have a very simplistic setting where you have doing something like this, you can easily create a semi-automated labeling algorithm. So you just say, well, this guy is going to match to this is going to match to that. You match maybe 3 or 4 of these points, and then you run a very simplistic algorithm that just completes the matching, and you use that for labeling. Okay. We need to move forward here to make sure we get everything done. Here is yet another example. This is another work we've done at NIPS last year. Other types of matching problems when you have near isometric matching cases. So you can also improve on by doing this predicting learning for near rigid objects. You just change the types of features you have and type of inference you use junction trees and structured SVMs as well. This is another thing. Well, we just submitted this, but I discovered today that it wasn't accepted at ICCV. But anyway, so this is trying to do something interesting. Recently, Belongi group in San Diego, they've used conditional random fields to do joint object categorization. What's joint object categorization? Imagine, just for the sake of simplicity, that you could segment this image properly, okay? So you could segment this into, you have here 4 disjoint regions, but you don't know the labels of those regions. You don't know what they are. But assume you could segment them properly. As a matter of fact, in order to assess the quality of different algorithms, you need to assume that the segmentation algorithm is independent of the model. So let's just assume you can segment this properly. And the question is, which object is this object here? Which object is this and this and that and that? Okay. So, of course, you could think that, I will create a Rhino classifier, will create a vegetation classifier, a sky classifier, a ground classifier, run those classifiers and predict things, right? But that's kind of something simple, because actually you know that if you see a Rhino, it's likely to be above and not underground. Whether it's likely to be under the sky and not over the sky. So different labels of objects, they don't occur independently in images. So if you want to predict things, you would like to leverage a data set that in that particular data set, you have labeled instances saying, well, these rhinos are under the sky, over the ground. Or if you see water and you have something big over the water, you know that's likely to be a ship, not a car, something like that. So you want to leverage these correlations, right? so that when you do prediction, you predict an entire combinatorial structure in the output. You don't predict independently this and that guy. But of course, that creates problems because you have a combinatorial problem to solve, right? So essentially, you have a more sophisticated predictor, but yet you can calibrate that predictor using training data. So that's the point. So in this work, we are substantially improving on the work of Belongi and collaborators. So we'll have to find another venue to stick this stuff in. So here, so this we just submitted as well. So what we are trying to do in this case, no images here, but there is a plot. Assume you want to do graph matching. Typically in graph matching, you make some assumptions. Like for example, I want isomorphism, I want homomorphism, I want isometries. There are all sorts of types of assumptions that people like to do when they do graph matching, depending on the type of the problem. Okay. So what we do here, we become completely agnostic with respect to those assumptions. And we parameterize everything, right? And we have a unified model where we just learn the weights of everything. So for example, in this case here, we have shape context features, 60 of them here. We are learning the importance of that. And in this corner here, we are learning the importance of isomorphic features, isometric features, homeomorphic features, all the different types of graph matching aspects that you can think of. So there's no point more in talking about, this is an isomorphic graph matching problem, this is a homeomorphic graph matching problem. This is just a graph matching problem. You parameterize everything, you learn, and then here is your soft description of your graph matching problem. Okay? And of course, when you do that, you substantially improve on results existing in literature and all that. Okay, so conclusions for this first part. And this is the main message I want to pass today. The second part is a bit more technical, but this is the main message I want to pass, which is if you have simple prediction problems like classification, you want to classify objects. People in general use simple models like support vector machines, right? And perform learning properly. So people know how to, computer vision people have learned already how to master these techniques here, okay? And the results are improving. However, when you have complex prediction problems, think of graph matching, think of image segmentation, MRF, stereo, and all that stuff, okay? People use complex models, but yes, they are starting to use learning, but they're still not leveraging all the data that you can leverage here. So most people actually still overlook learning in this case. And maybe you can still overlook learning if you have a stereo matching problem where, assume you have a monochromatic image. But imagine 5 or 10 years down the road when every image you get, even in your webcam, will be hyperspectral. You will have 72 channels. How would you manually tune the stereo parameters for 72 channels? You better start thinking ahead of time and automatically learn all this stuff, okay? So the take-home message is there exist techniques that allow doing both things, complex models and learning. That's the first thing you should take from this talk. And the second thing is that in this trade-off between model complexity and data leveraging, if you think computer vision is still far to the first side. So we are using very complicated models, but we are not leveraging as much data as we could. Okay? So I think a better balance is possible here. We should ask these questions. And give.
This is just driven by the history of the data that we have. Like we didn't have ground truth stereo data sets.
I agree with you. That's true.
Label me data set.
That's
a lot of things.
That's
things
true.
Are just coming online just in the last few years.
That's
why.
That's completely legitimate argument, but there are 2 points here. First is that that's true, but that's not the whole story, okay? And second, even in the lack of completely labeled data, you can still use this stuff. Yeah. So basically, you can use a semi-supervised version of this. But of course, for that, you need to work hard because you need to look at the last 2 years papers at NIPS, understand all that maths. And
see, that's the problem is you guys haven't been working fast enough, of course.
different questions. We've been working on different questions. I just think that since I'm mostly a machine learning person, applying my stuff to vision, the way I see it is that, look, let's talk to the vision guys and say, look, we have these tools, okay? And we can really change things by using these tools. So let's try to talk to people and try to excite people about using these tools. Yes?
My question is that while you are leveraging the training data to tune the predictive model such that it can fit the data well, the risk is that your model will be tuned specifically to the training data, while it may work poorly for the other things that
well,
are similar to.
in practice, we use, you just do regularization. I mean, I'm not talking, this is not a technical talk, right? But in practice, you don't minimize only the loss on the training set. You minimize the loss plus a regularizer that's basically constraining the model class. It's saying, well, I'm not going to learn an arbitrarily complex functions. I'm going to learn functions that are meet, they do well on the training set, but they're also sufficiently simple. You just do regularization in practice. Okay, so this is the main message I had for today. So since I still have 15 minutes, let me just tell you a few other things that we are doing. So this is something I'm excited about because we just submitted this stuff. It's very recent. And it has an application in computer vision. Convex relaxations of mixture regression applied to motion segmentation. So here's a motion segmentation problem. So this is supposed to be just a single image of an image sequence, okay? So I have this car is moving, the other car there is moving, and you have the background here. And the fact is that you want to segment these motions. So you want to classify, this is the ground truth, let's put it this way, of this segmentation. You know that this is one motion, that's another motion, that's another motion. Okay. The motion models that we have, like you want to estimate fundamental matrix and all that stuff, they're all linear regression problems. Okay? So if we knew to each of these three motions, every one of these features belongs, we could solve a simple linear model that will estimate that motion simply, just by doing least squares regression. Okay? The problem is that we don't know. The problem is that we don't know that this guy here and this guy here belong to the same motion. We don't have this information. In fact, the motion membership for every one of these points is a latent variable that can attain 3 values in this case. But we don't know what it is. Okay? So how do you solve that problem? If you observe the membership, you have a nice convex problem that you can solve closed form, least squares. But if you don't know, how do you solve it? Obviously, this will also be a very complicated optimization problem because this will be a combinatorial optimization problem. You would ideally have to look at all the possible configurations of 3 motions of these points, which is an exponentially large set, and solve the regression problem for each one of those, and find at the end which configuration gave you the best fit, the best least square solution. Of course, you can't do that in practice. So what do you do? So I'll tell you what people do. So this is the setting, okay? So we have, just in a more visual way, mathematical way here, you have mixture regression. Here's a bunch of points. Here's another bunch of points and another bunch of points. If you knew that this belongs to the same line, that this belongs to the same line, and this belongs to the same line, you just solve 3 independent regression problems. But you don't know that. Okay, let's just assume for sake of simplicity that you know there are 3 models. Okay, you don't have a model selection problem. You know there are 3 models. You know there are straight lines. But how do you solve this? So what's the typical answer? Well, the typical answer is, well, you have a latent variable for each one of those guys, which is the membership of that point. So people just, okay, this would be a good solution. Okay, and people just use EM. That's what people do. So what do? You pretend you know a first solution. Then you solve your problem. You use that solution to initialize and then solve for the membership again. Then go back and re-estimate the model. And then solve again and re-estimate the model. Well, we know very well that this function that EM is trying to optimize is a very highly non-convex function, which is full of peaks and valleys, and moreover, it's discrete because we are optimizing over the discrete space. So it's piecewise constant function. It's the worst possible optimization problem you can have. So is EM going to do well? Well, if you can afford for EM running over.
Is it discrete, or can you have soft assignments in EM?
No, you can. In EM, you have everything is soft assigned at the end. You discretize. Okay.
So I can believe there's lots of local minima, but it's not actually a discrete optimization, combinatorial optimization.
Oh, the original. One thing is the problem itself. The other thing is the model.
Right, so
The problem is discrete. The model is soft, exactly. But still, it's really well. You can easily. I'm sure many of you have at least maybe implemented EM once in your lifetime or whatever, and run EM, and you can see that EM can really do very badly. It can do very well, but it can do very badly. And the reason why EM can do very badly is that because it's finding really poor local minima. So how do you go and solve this? Okay, you can try to do EM, or you can try to do something else. So here's something else we're trying to do. We're trying to, instead of, we have a very complicated function here, very high dimensional multi-modal function, and you want to find the global optimum here, something, okay? Your global optimum. And then EM, and EM is gradient descent, basically, okay? So if you initialize here, you are going to find this point. If you initialize here, you're going to find this point. But there are millions, billions of values here. So depending on initialization, you're going to do well. Depending, you are not going to do well. Okay. So what we do, we construct a convex upper bound on this function. And instead of solving this problem, we solve this problem. So we change the problem. Yes, is that bad? Well, of course, you're not solving the original problem. But the question is, if we happen to construct a convex upper bound whose minimum of this convex function is not too far from this minimum here, you've really gained something. Because solving this is easy. And you obtain the same solution that you would have obtained if you could have solved this problem. Okay? So before telling you the good news, I'll tell you the bad news. The bad news is that there is no existing algorithm I'm aware of that tells you this the deviation between this point and the optimum of this point. All what you can do at the moment is construct a convex upper bound, which is sound in an intuitive sense, but you cannot really give many guarantees on how this solution is close to this solution. Okay? So that's the bad news. So the good news is coming now. So we construct this convex upper bound on this objective function here. But remember, this thing here is very misleading because this problem is extremely high dimensional. But still, that's a convex function. We know how to optimize convex function. There is nice technology to do that. In particular, this is not a simple gradient descent kind of unconstrained optimization problem. This is a semi-definite program. And among many possible convex optimization problems, this is the one of the worst you can have. Okay? This is not going to scale. Basically, you can solve this for 300 observations, 400 observations. You cannot solve this for thousands of observations. So this is not good. Typical interior point methods, so barrier type methods that solve this problem. So you essentially enforce the constraints in the objective function by a logarithmic barrier, doing all those tricks. Okay? And then this is extremely expensive because it's actually cubic on the matrix of on the square matrix. So it's ordered 6. It's going to be really bad. So that's what we do. We reformulate the original problem as a semi-definite program, okay, which is really bad to solve. But we figure out 2 ways of solving this problem exactly without doing semi-definite programming. Okay? So we bypass completely the need for using semi-definite programming. And this is only possible because of the very structure of this problem. It couldn't be possible in general. So here is, I only have 5 minutes. I won't go much in detail, but I want to give you the intuition of what's happening. So every one of those observations I mentioned previously, let's call them xi, you have a latent variable for them, which is zi, which is telling you, well, to which motion that particular observation belongs, okay? So now you construct this phi variable, which is just a tensor product of these two guys. So this is not known. This is partially known. This is known, but this is not known. So this vector here is this tensor product of this thing that you know with this thing that you don't know is something that you know partially only. You don't know it completely. And now you can easily, if you have this notation, you can easily write the mixture regression problem, which is a mixture of regression problem, simply as a regression problem. So here is your prediction, here is your observation, here is a model. So you have just an inner product of your vector with, or parameter vector with phi, and you have a, we assume in this case least square. So basically you have you assume a Gaussian noise in your data. So here is the noise model, okay? Classical regression, just that the key difference is that here we don't have xi, we have psi, which is something that you don't know completely. Whereas in traditional regression, you would only have xi because you don't have this class membership issue. Okay. Well, it turns out that you can reformulate all this stuff in a nice matrix form. Here you have a quadratic objective. Here you have a linear objective because all that's a nice Gaussian exponential family. Everything becomes quadratic or linear. And here you have a regularizer which addresses the issue you've mentioned previously. So we want to penalize models that are complicated, essentially. So we have a Gaussian prior on the parameters. Okay. And what you want to do, you want to actually, well, there is some notation problem. This is this variable psi here. We want to solve, yes, we want to solve a traditional least squares problem on W, okay, for a fixed psi. But psi is not fixed. So we need to jointly optimize on this, we need to jointly solve this linear regression problem and this combinatorial problem. Okay, so this is the original objective. That's, as I mentioned before, very difficult. You cannot discrete and all this stuff. So after lots of maths, you can prove that this is a nice convex relaxation for that problem. And I won't give you details, but essentially what you do, you compute the dual of that original problem, use Fenchel duality, and you do a few math tricks, and you obtain this optimization problem here. And this problem is a convex problem, okay? Essentially, you are optimizing over C. This function here is concave in C, because it's square negative here. It's concave in C. And then you have a semi-definite constraint here, because this matrix M needs to be positive semi-definite. It needs to have bounded eigenvalues and all that, blah, blah, blah. The point is that you have a semi-definite program, but it's hard to compute, to solve. This is an exact reformulation of that problem. So if you solve this problem here, if you solve this problem here, you will recover the same solution than if you solve this problem here. But solving this problem is very expensive. And solving this problem is very easy, because this part here can be solved by basically eigenvector computations. It's cubic. You can solve this part efficiently. And this optimization over C can be done by gradient descent. So essentially what you do, you alternate eigenvector computation with gradient descent, and this in practice does really fast. This version of our reformulation runs as fast as EM, basically. And then here's the algorithm, blah, blah, blah. You need the input, which are those parameters of your noise model. You need to solve eigenvector computations. You use BFGS, just non-smooth convex optimization, traditional, standard convex optimization tools. But this is much more efficient than doing semi-definite programming, than using interior point methods. It's much faster. So this is scalable. You can solve this for thousands of points. Okay? This is the first reformulation. You can find another convex reformulation of the original semi-definite program. And this is the ugly looking of that thing. But you can prove that this is also a convex optimization problem. You have also a semi-definite constraint here, but this semi-definite problem can be solved efficiently as well. it is not as fast as the other one. It's about 3 times slower than EM. Okay, so here's the algorithm. Okay, I don't want to go much in details, but here are some pictures. Let's close with some images. So here we have a few data sets from Motion. And here's the first data set where this is the ground truth. And if you run EM, you run the first reformulation, the second convex reformulation, you obtain, this is a sort of an easy problem because EM is finding the optimal solution already. These guys also end up finding the optimal solution. Now you have a slightly more difficult problem here. And then you can start to see the differences. You observe that EM does a few mistakes here, another mistakes here. And this convex reformulation seems to be at least as good as EM. Is doing quite well. And this one here technically should find the same solution because these two guys here are solving the same problem. Okay? These differences here are basically numerical differences. Here's the ground truth. Here EM does pretty badly here, has all these mistakes here, over there. And here with this convex relaxation, you still are far from the original ground truth, but at least you make much less mistakes here. And you can quantify, you have tables showing details,
How do you initialize EM?
Oh, we run EM 100 times, initialized randomly. So that's the setting. Okay, we could run EM. This is the best out of 100 iterations.
The other ones are only once.
It's a convex problem. If you solve it 100 times, you get the same solution.
Okay, so the min-max convex, when you said it was same speed.
The max min, yeah. This is about the same speed.
As a single iteration of the EM or 100 iterations?
No, as about 100 iterations of EM. Okay, so being fair here. Of course, you could run EM for 10,000 iterations, but then it's going to really be slow, right?
Well, yeah, I mean, if you've got that many points, the number of iterations you start with is really going to not make a lot of difference because they're possible. I mean, well, you've got 2 to the 30th or 40th or 50th.
Well, in theory, yes. In practice, you see that you can get a difference if you use 10 iterations or we found difference between 110 iterations. Yeah. Okay, but we didn't really run experiments with 1,000 iterations to know the answer.
And what happens when you take the max min convex and then use that to initialize EM?
Well, it will find the same solution. Well, you mean use this solution to initialize EM? Yeah. Well, we haven't done that, but you don't really want to do that because that will be really expensive. Because you have to run twice the problem.
Well, just one iteration of EM, so, or
Yes. Yes, but use this. This is something that people do, initialize this because you could have hit this point maybe, right? Maybe you were here. It's a very valid question. I mean, we haven't done this. You could have hit this point here. Yeah. Okay. So you are minimizing this function, right? But you are not minimizing the function that you really would care about. That's one thing you can do. Haven't done that. But yes, definitely you can use this convex relaxation and initialize it.
Right.
Yes?
Another way to see it is to just compute the energy of your model, of the solutions for each of these techniques and see which one is lower.
That's true, but there is a slight tweak to that, which is the following. There are hyperparameters in our model. Okay, you have this alpha and this gamma here. You can either choose to cross-validate those parameters. If you want to cross-validate or do some parameter search, at the end, the best EM result and the best convex relaxation result may be for slightly different models. And then your score may be different. Okay? But we are still in initial experiments with this. One thing we want to do is, just let's stick to the same hyperparameters and do a very, thorough analysis and see what we.
So hyperparameters. Sigma is the noise.
Sigma is the noise. Okay. So gamma. There's one caveat here. We need an extra parameter than EM. We need this gamma. What this gamma is telling you is the class balance, the balance between the sizes of the classes. Okay. This is sort of gamma is an upper bound on the size of the largest class. So if you want no class to be larger than 50% of the points, you need to have that gamma. So we don't really have a solution for avoiding that. Okay, but this alpha and this so this sigma is totally a property of your data, right? But alpha not. Alpha is a parameter of the model. Okay, so you may end up with slightly different guys if you cross-validate them. If not, then your point is valid. Okay? So overall, and we have many of other motions. I'm just showing 3 here, but in our submission we have appendices and all this stuff with many other things. And especially the max mean, because the max mean is quite fast. And it seems to preserve quite a lot of the structure of the problem. Right? Okay, so yes?
Question on this. I mean, what's moving here? Say the bottom sequence. Just
the camera?
The camera's
That's why you have all these things, this green here, the car and that car.
And how many images you have? I know that this middle one, I mean, it's a twice sequence really, but there are only a small number of images there, right? What about this one on the bottom? Just those images?
No, there are more. You have to ask the student to implement this. I don't know. I have to check this. I don't exactly know how many points here. Yeah.
How do you know the number of mixture components?
Oh, that's a big question. We don't. So these are 2 fundamentally different questions. This is a model selection question. Okay. So there's no way you can use a likelihood criterion to optimize that, because likelihood is monotonic on model complexity. Okay. So if you make more complex models, you're always going to obtain a better likelihood. Okay. That's a fundamental question. That's a philosophical question. That's the problem of induction in science. So it's an open problem, and you can use several different model selections, MDL or whatever, or you can try to be Bayesian and do all these hierarchical Bayesian stuff. Because if you are completely Bayesian, then you have no model selection problem. You just put a prior and keep running, and So can you speak up a little?
For EM, you can use AIC, BIC criteria.
AIC, BIC are model selection criteria. That's exactly what I'm saying. The models, you are right. You are completely right. The advantage of EM is that since we have a probabilistic model, you can be as Bayesian as you want. Okay, so you can do what you're saying. In this setting, it's not obvious how to do that. I don't know the answer. Any other questions?
Well, I don't really
Yeah.
know much about this, but I remember a long time ago, like more than 10 years ago, I think Blake worked on something called graduated convexity.
Graduated assignment. No? Or graduated convexity?
They call it
Graduated non-convexity was a continuation method. And those
Continuation.
were
Okay.
popular in the vision community in the mid to late 80s.
Oh, okay.
There's Blake and Zisserman and Dritsopoulos worked on this.
Okay.
But they were for regularization problems with non-quadratic energy
Oh, I
functions. So they would...
And non-convex as well? Non-convex or
non-convex. So you would introduce a graduated non-convexity,
Okay.
basically.
Okay. I see.
Yeah. So it's continuation methods.
I don't know whether it's not related.
I don't know if it's related or not. I mean, it might be, because there's this idea, at least at the philosophical level, right, of sort of having an approximating function that is smoother.
Yes. You've compared this with the EM, right? And I think maybe that's not perhaps the state-of-the-art method here, right? I mean, for this particular problem, I mean, maybe your techniques are more general.
What would be the state of the art?
Well, you look at the recent papers of René Vidal. I mean,
Yes.
he and I have a couple of papers.
Yeah,
on
I know.
And, well, there are
Yeah.
sort of methods of Canatani, for instance.
Yes.
We don't look it up, but which are imposing an affine model on this, and,
Right.
and then there are an affine model, and then the whole thing becomes linear, and then it's sort of like what René calls a generalized PCA
Yes.
problem.
Yes.
Right, and then we sort of look at it in that technique. And he also has more recent papers. I think it's CVPR 2009, I
Right.
believe, Right, so that's obviously what
That's
you
good.
wouldn't have seen.
Okay, maybe I'll talk to him at CVPR.
Which they're using, in fact, some sort of compressed sensing technique
Okay.
in a way to solve the GPCA problem. So that, when looking at the results, the numbers in this paper, they're fairly amazing. I mean, it makes me feel ashamed that we've actually, he and I have published the previous paper because it just kills it, right? Nevertheless, there are, you should...
I need to look at that because remember, this is a hammer that we're looking for a nail, right? We are not solving the motion segmentation problem. We are solving the mixture regression problem. And we are modeling motion segmentation as mixture regression where you have a quadratic criterion, okay? Probably these models, they are different models. They are not the same model I proposed here. The very first slides I put up, okay? So this is a quadratic, basically regression problem. So they are different models. So I would have to reformulate new convex relaxations for every different objective.
Okay, well, I suppose...
Yeah, I'm actually technically done. So if you...
Well, okay.
Yeah.
Tiberio is here today, and we haven't actually, haven't been away, arranged a lot of talks on, but it'd be nice if we could talk maybe with some of the interns and things like that, as well as the other people here. So let me know. Maybe I'll try and best to talk to them as well.
Okay, thanks Richard, thanks Rick. Yeah, thanks everyone. Okay.